Welcome back to Tech 293 for the second video for Tuesday, February 16th. In this video, we're going to talk through Lab 4, how you're going to do Lab 4 and acquire the data that you're going to use to make stress-strain curves and answer the questions that are in Lab 4 in the lab manual. So basically in Lab 4, we're going to take a bunch of plastic specimens, 4 different types of plastic specimens: high-density polyethylene, polypropylene, like what this is right here, polycarbonate, and glass fiber reinforced polypropylene. And we're going to get a bunch of data on those. We're going to stretch them apart until they break. And then you're going to get all the data, and you're going to calculate stress-strain curves and answer the questions in Lab 4. So in this video, I think I'm actually going to work kind of backwards. And the first thing I'm going to show you is what your results should look like. So when you do Lab 4 on the Instron machine, it's going to be collecting data as it's pulling these specimens apart, and it's going to be writing all that data to an Excel file. And I will share that Excel file, all of the Excel files, with you on RegNet. There's going to be a different file for each test. And the Excel file is going to contain the force data as well as the extension data, as well as the time, which you don't really need. And you're going to need to convert the force data into stress and the extension data into strain so that you get stress and strain data at each data point in the test procedure. And then you're going to need to create stress-strain curves. And those stress-strain curves are what you're really going to use in Lab 4 to answer all the questions. So I'm going to go ahead and share my screen here, and I'm going to give you a quick tutorial on how to use those data files that you're going to get from the Instron machine and use those for Lab 4. This, hopefully you can see, is an Excel file. This is what the raw data is going to look like. I just pulled one of the raw data files from last semester, and this is what the data will look like. This is, I think this might be HDPE, but I don't remember. It doesn't really matter. So the columns that you're going to see in your raw data that you're going to get from RegNet, by the way, I will upload the data from the computer in the lab to RegNet. So you'll be able to access your raw data from RegNet. And you can see we've got 3 columns on here. The time, which you can ignore, like it doesn't really matter what the time interval is for us. But if you're curious, that's the amount of time since the test began. This is the extension, in other words, the change in length of the part. And this column is the load measurement in pounds force. So that's the force. All right, so what you're going to need to do is create some new columns for stress and strain. So it doesn't matter which column is which, but here extension comes before load. So I think I'm going to do strain in this column. And of course, the units for strain are inches per inch. And in this next column, I'm going to do stress. And of course, the units for stress that we're going to use are PSI. All right, so I'm going to calculate this whole column, and I'm going to populate it with strain values. All right, so what is strain? Strain is the change in length divided by the original length. And I haven't told you these original dimensions yet, but I'm going to tell you them right now, and I'll tell you again when we go through the lab paper. But I'll tell you right now, the original length of the gauge length section here is 2.25 inches. I had to double check that, but that's right, 2.25 inches. So in this cell right here, I'm going to write an equation equals the change in length, which is this cell, divided by 2.25 inches. All right, so that gives me my strain value. And that's my strain value for the very first data point in this data series. All right, now you don't have to type that over and over and over again. You can just grab that and your icon turns to something that looks like that shape. You can drag it down, or you can save even more time. When your icon turns to that shape, you can double click on it and it populates the whole column of data. So there's all of my strain data for this test. Now for stress, stress is force divided by area. So this is going to be equal to the force, which is this column, divided by, and now I need to get the area. So I'm going to take parentheses, and the cross-sectional area here, the dimensions of this thin section in the middle, the dimensions are 1/2 an inch in this dimension and 1/8 of an inch in this dimension. It's 1/2 inch by 1/8 inch. So I'm going to type 0.5 times 0.125, which is 1/8. So notice I have C3, which is the force, divided by the quantity in parentheses, 1/2 times 1/8, because that gives me the cross-sectional area of the part. All right, so there we go. That is my stress value. So once again, I can drag this down like this to make it populate the cells, or I can just double click like that and have it populate all the cells. So now I have all of my strain and stress values for this test, and that took me, you know, if I wasn't explaining it and talking about it, that would have taken me 2 minutes at most, All right, and then what you're going to need to do in the lab report is create plots. So there's different ways to create plots in Excel. What I like to do that I think gives me the most control is go to Insert and then click on the plot icon. And it's the plot icon for a scatter plot. So this is going to be a scatter plot. And here I select a scatter plot. All right, so there's my scatter plot, and now I'm going to select the data. So I like doing it like this because it gives me control over exactly what data is on the x-axis, what data is on the y-axis. So I just right-clicked in here, right-click and select data. And now I'm going to add an entry. And now it's going to ask me for the series name. I'm only going to have one series on this plot because you need to make a different plot for each of the different materials, HDPE, polypropylene, etc. So you don't really need a series name if there's only one series on this plot. So I'm not going to even put anything in that box. So the X values, remember our X values are our independent variables, which are strain variables. So for here, you click on this little icon here, little icon there, and now you can highlight all of the cells that you want to be your horizontal axis. So that's going to be our strain values. So I'm clicking there, and then I'm going to drag all the way down here. I don't know that there's a shortcut for this, so you just got to drag all the way down. Didn't take that long. There's our strain values, and our Y values are our independent values, and that is going to be our stress value. So I'm going to click here and then bring it all the way down, and there we go. You know, actually I just noticed one thing. You see how some of these numbers here are negative, and you'll see what that looks like when I click on this and click OK. Click OK again, and now we get our plot. So here's our plot. Here's a stress strain curve for HDPE. And some of these plastics, it's more difficult to identify the linear elastic region. You got to use your judgment. So if I were to look at this, I'd say the yield stress is probably somewhere around right there. But it's a little bit subjective. The plastics are a little bit difficult to identify where exactly the yield stress is. Metals are a lot easier to identify where is the yield stress. Ultimate tensile strength is up here at the maximum. Failure is right there. So what happened with these negative numbers is we were doing the tensile test and then it failed, and then there's kind of like a rebound effect. And so it actually reads a negative number sometimes after the part has failed. So that's kind of nonsense. I mean, it's not really even testing the part at that point. The part's failed. So what I would probably do actually is come down here and I would delete all that negative stress data. So I'm going up until I find the first non-negative. All right, so all these stress values here are negative, so I'm just going to delete those. Right click, delete, there, and I just deleted all of them. And so now my stress strain curve looks a little bit prettier. It doesn't have those data points down here, which were meaningless because that was after the part had failed. All right. So make sure with your plot, make sure you have a chart title. Make sure you have axes units and labels. Let me tell you the easiest way to put in axis labels. Go to the chart and then click on design and then click on add chart element down here, and now you've got a whole list of, you can add axes, which are already on there, axis titles, so you would need to add those for the primary horizontal. You see what that does right there when I click on that? So now I have an axis title, so you can fill that in with units. Make sure you got units in there. Same thing with the vertical axis, and then change the chart title as well. All right, so you'll need to do that for each and every one of the 4 specimens. After you do it the first time, it really doesn't take very long to make these stress strain curves. Honestly, 5 minutes a piece at most. All right, so that's the demonstration in Excel. I hope that's helpful. I typically get some questions most semesters on how to create these plots. So hopefully that is a pretty good explanation of how to create those. All right, now I'm going to switch over to the document camera, and we're going to talk through the lab itself, which is how to get that raw data in the first place. All right, so lab 4 starts on page 39 of the lab manual. Your specimens are going to be these 4 specimens right here. I will hand them to you in the lab. I'll give you one of each to do the test. Then you're going to go to the Instron machine. I would recommend that one person install the test specimen, this thing, install it in the Instron machine, and have another person in your lab group sitting at the computer, operating the computer. And then when you're changing specimens, after you do one specimen, then switch off who does what. That way you each get experience loading the specimen in the machine, and you each get experience driving the computer, getting the computer test set up and going. All right, so step 2, you're going to need to install the tensile test specimen in the jaws of the Instron machine. No, sorry, that's just install the testing jaws. That'll already be done for you. Step 3 will already be done for you. That's just setup. I will already have that done for you. The testing procedure then is to measure the dimensions, but actually to save time, I'm not going to have you measure the dimensions. I'm just giving them to you right now. They're all the same because they all use the same mold in the injection molding machine. So all of these specimens, we call them dog bones, they all have a thickness, that's this dimension, of 1/8 of an inch. They all have a thickness, that's this dimension, of 1/2 inch. And they all have a gauge length of 2 1/4 inches. So you should write that down so that you have that for later reference when you're doing your lab report and your calculations. All right, then now this step 2. This step 2 is when you're installing the specimen into the machine. And you need to, there actually are arrows. I wish I could show them to you right now, but there are arrows on the jaws that tell you which direction to rotate the jaws, to tighten the jaws, and to loosen the jaws. And I know this sounds simple, but actually it's not. It's pretty common for someone to mix it up, and then we'll start the test and we're not getting data, and it turns out the jaws just weren't tightened. So that's something that you'll just have to look at on the day of the lab, and I'll point that out on the day of the lab. But anyway, in step 2, you're going to install the test specimen into the jaws of the machine. And then in step 3, you go to the computer, which is right next to the Instron machine, and it's going to have the Blue Hill software. That's the software that interfaces with the Instron machine. And you're going to click on the test button, and you're going to have to click on the test program. And the test program is going to say TEC 293 plastic tensile testing in the file name. All right, that's the testing procedure. And then it's going to ask you what to name this data file, and you want to name it something that you can identify later, because I'm going to upload all of the data from all of your lab groups into ReggieNet, and so you need to be able to identify which files are yours. So don't just name them polypropylene tensile test, because then we don't know which groups it is. So in the file name, put in your names along with the specimen, like the example shown here. Okay, then click Next. And then this is really important. You can see step 8 is in bold. It's really important here to zero out the machine. It's kind of sort of like calibrating the machine before you start the test. So you got to balance the load. That resets the load measurement, the force measurement, to 0. And then the second part here is to 0 the extension. That resets the change in length to 0. So you got to zero out the machine. Otherwise, your data is not going to start at 0, and that would be a problem. All right. Then you press Start on the computer, and then it starts running the test. And it's kind of neat because you'll see on the computer, you'll see a real-time update of the stress strain curve on the computer screen. It's kind of fun to watch. Now the test specimen will eventually fail, and the computer is trying to find where it fails, and if it can pick up and identify where it fails, it'll stop the test automatically. And the way it's going to detect that is if the load on the machine drops suddenly from one data point to the next. If it drops by 40%, it will identify that as a failure of the part, and it will stop the test. But sometimes if you get a lot of necking on the machine, then it won't detect when the part fails. If it's a real gradual failure, then it's not going to detect that. So at some point, if you get a really, really long specimen, if you get a lot of necking, like if you get something like this, then eventually we'll probably just stop the test in the interest of time, because this is pretty slow. It's a pretty slow process. Then step 11, when you click Finish on the computer screen, that's when the computer actually saves the data. And then you remove that specimen. And then if you have more specimens to test, then it's going to ask you if you want to repeat the test with another sample. And if you do, click yes. If not, then no. And if you do, then go back to step 2 and redo this whole procedure until you've done all the 4 specimens. All right, so that's the data collection. That's all of the data collection. Now we get to the results and the lab report. So in the results, you need to construct a stress strain diagram, just like I showed you. I showed you a majority of it anyway. I didn't finish it, but you need to make sure that you label all the axes with units. The horizontal axis should be strain. The vertical axis should be stress. Make sure you use engineering stress. I want you to label the plot where the yield stress is reached, kind of like this. So your plot should have axis labels with units. You should have a title up here. You should label the curve where the yield stress occurred, where the ultimate tensile stress occurred, and where failure occurred. And then underneath the plot, you should label it with a figure number. Figure 1, stress strain curve of HDPE, something like that. All right, then I also want you to calculate the elastic modulus of each one of the specimens. And I want you to show or describe your calculations, and then make a table. Make a table showing the yield stress and the ultimate tensile strength for every material. And this is based on your experimental data. Once in a while, I'll get someone who will look up on matweb.com or use some reference data and give me that data. But no, I want your actual experimental data for yield stress and ultimate tensile strength. And then for each material, calculate the maximum elongation before it failed and show that in a table. And you can use this equation to calculate the percent elongation. Okay, then the discussion section, which should be in complete sentences. And the first part, I want you to just compare and contrast. So this should be a good solid paragraph. And I want you to explain and justify your answers. Don't just answer, oh, this was the strongest, this was the least weak. Explain to me how you know. Probably by looking at your curves, but what about your curves tells you that one of them is the strongest, one's the weakest, etc. So I want you to tell me which one has the highest elastic modulus, which has the lowest, which has the highest yield strength, which has the lowest, which has the highest ultimate tensile strength, which has the lowest, which was the most brittle, which was the most ductile, and which was the toughest and which was the least tough. So for each one of these, don't just give me an answer, tell me how you know the answer. Justify or explain your answer. And the next couple are just application questions. In the next one, let's suppose you were in charge of designing a plastic hard hat. And in real life, they really are plastic. And based on the materials that you tested in Lab 4, which one would you be most likely to choose for a hard hat? Number 3 is similar. If you're having to choose a material for a car bumper, which material would you choose? And the last one is, let's say you're designing a buckle, like a buckle for a backpack or something. If you want to make this part, what material of the 4 that you tested in Lab 4, which material would you choose and why? Explain why. All right, so that is an explanation of how we're going to do Lab 4 and then what you should do with that data after you do Lab 4. When you come in to do Lab 4, either on Thursday or next Tuesday, make sure you bring a face mask, make sure you bring your safety glasses, and make sure you bring your lab manual as well, because you're definitely going to need to follow along with this lab manual as you're doing Lab 4. So make sure you have this to follow along with. I'm really looking forward to Lab 4. I hope you are too. It feels like it's been a little while since we've been in the lab, so it'll be good to get back in the lab, start using the Instron machine, and start breaking some stuff. So that'll be fun. All right, so I look forward to seeing you in the next week or so, depending on when you're coming into the lab. So I'll leave you with that for today, and I will see you soon, either on Thursday or on Tuesday.